Hello GGS 300, welcome back to the 13th lecture. So today we're going to be covering correlation, and then within this more theoretical lecture that I'm going to give you now of these kind of theoretical and empirical concepts that we're going to basically cover, we're then going to tap out some code in the next session, in an R session in the laboratory, which I think will be the 10th session that we've done so far, and then hopefully you will have all of the content that you need in order to succeed this week, okay? So I thought we'd just take a couple of minutes in order for us to kind of recap and cover what we've got coming up, okay? So I think I spoke a little bit briefly about this, but it's important for me to also just kind of give you a bit of an indication about what's going to happen towards the end, this final part of the term, okay? So here we are, week 13, November the 15th, and this week we're covering correlation. We've got lab 10, and you've got the assignment number 10 as well. You've got McGrew et al. Chapter 16 to cover. And we then have this Thanksgiving recess, okay? And then we have this final session on regression, which will be the following week. And then we'll have the final exam, which basically is on December the 6th, around that kind of week. So it won't exactly be on December the 6th, but it will be around that time, okay? So I'm going to set the correlation assignment this week, and then it will be due, as we're not here next week, I basically made it Monday, November the 29th, okay, so that's almost 2 weeks from now. So hopefully that's plenty of time for you to complete the work. I didn't want to set it so that it was due on November the 25th, which was it the next Thursday, basically, a week on Thursday, November the 25th, because I'm pretty sure that's Thanksgiving Day, okay? So I didn't want that to clash with your ability to, you know, see your family, see your friends, have some time off. Kind of get a little bit of rejuvenation under your belt before we kind of finish the final part of term and then move into the examination period. Last day of classes, so technically it's going to be December the 4th, and then I think you have like 2 days of reading, which just allows you to do some prep before the final exam. So the final exam will be sometime around December 12th. Now, I'm not giving a fixed date for this yet, and I know one or two actually reached out to me asking when the date will be. But the reason why I do this is I'm trying to give you guys the most amount of time to succeed on this course, right? So I will basically provide you with a finishing date for the final exam, which is like the day before, the day that I have to submit the grades to GMU, okay, to GGS for your final grades for this. And I want to give you as much time as possible to do the assignments that we've got, and then also time to revise for the classes. So there'll also be a set of ungraded tests which will go along with that final exam, just to prepare you basically. So I don't want to give you all of the the assignment dates in one part of the semester. I'm trying to space them out, and I'm also trying to give you the maximum amount of time to prepare for that final exam. So just bear with me a little bit. Once I get that final date, I'll get back to you and I'll let you know. But basically what will usually happen is I'll put the test up, and there'll be maybe 48 to 36 hours for you to be able to take it online. It'll be similar to the other tests, but you do need to make sure that you have RStudio available to you, because I will set you some tests that you need to carry out within that timed part of the exam, okay? So it's kind of picking up on some of those things that you've done previously within the assignments, but this time just to kind of fully make sure that it's kind of drilled into your brain, there'll be part of that in the exam, okay? So let me know if you've got any queries about this. I'll say more about the exam nearer the time, so don't worry too much about it now. Just focus on getting the assignments completed quickly and getting them in on time, and that will give you as much time as possible to excel, because you'll be able to prepare for the exams, and I'll give you a little bit of guidance as to what I'm expecting you to learn there. So this week correlation, next week regression. They're very similar to each other. But basically correlation is the precursor for then how we start to understand regression techniques, which will be fairly kind of core to any future statistical work that you're likely to do, because it's one of the kind of most flexible tools that's available to a statistician, okay? So without much further ado, let's get into the correlation content. So we know that we've covered most of this chart now, so I don't think we've been over here yet. But we've been all the way down here. We've covered T-tests, which will come up in the exam, ANOVA, We've then covered discrete and categorical, so non-normally distributed data types. And then we've also, today we're covering correlation analysis. So that's basically where we've got questions where we've got continuous data and we're looking at the relationships that are present and whether we've got true independent variables. And then eventually we'll move on to regression next week. Okay, so I think pretty much by the end of this, we'll have covered essentially every single box or close to every single box within this flowchart. So hopefully that's going to give you a fairly robust and comprehensive understanding of the statistical techniques available to you. It's also worth remembering this little kind of circular box we've got up here, this ellipsoid. Basically this is saying, you know, for the parametric assumptions, we need to make sure that we have independent, unbiased samples, which you know now because we covered that last week. For example, looking at things like spatial autocorrelation, how that kind of does not meet this independence requirement, which is always a problem for us. We need to make sure that we have normally distributed data. Well, you know that already, but also we need to make sure we've got equal variances, okay, across the data points. So look, let's move on. That gives you a good overview of where we're at, where we're going. Now we're going to be focusing on the kind of nature of correlation, okay, so this is thinking about things like covariation and relationship strength, direction, things like this. So what we've covered so far is kind of comparing samples to population parameters. Okay, generally with the kind of the exception of those difference non-Gaussian tests that we covered for categorical analysis, like chi-squared. So the main aim has been to look for kind of differences, but now we're kind of going to ask a different question in the remaining couple of sessions. So it's like, is there a relationship between two variables that might vary? So that's what we're going to be thinking about today, covariance. So before we were focusing on the difference, today we're thinking about the similarity between those variables. And we can test this using types of statistical approaches like correlation analysis, which gives us some indication of the direction of the association. So is it positive, is it negative, and also the strength of that association. So is it weak, is it strong, and we can quantify essentially those different aspects, as well as me being able to kind of qualitatively, verbally discuss that in general terms, and for us to be able to kind of eyeball relationships in this way, as we will do shortly. We can also do it quantitatively, which is really nice. So you'll get the formulae that allow us to actually encapsulate those types of relationships in that way. So the variables, importantly, don't need to have the same units, which is good. So that means you've got a really flexible tool that you can then use to assess many different things, okay? So, as I said before, we can kind of eyeball these relationships without formally testing them explicitly, and that's always a good kind of way to understand your data before you either do a correlation analysis or you do a regression analysis. And actually, I always remember when I was starting my PhD and I was in the first year or so, and there was like a much more advanced physicist who at the time I think was a senior postdoc, a senior researcher, and he obviously was highly quantitatively capable, but he would always say, you know, the very first thing you need to do when you get a data set is not some really complicated statistical technique. It's actually just looking at the correlations between those variables in relation to your key outputs, okay? So you just need to like map them and understand them in this way, and that's why this is such a key technique, okay? So even if you go on and do lots of really fancy statistical analysis, the very kind of first place you want to start is by looking at your output variables and then basically looking at the relationships that your other kind of independent variables might have in relation to this one thing that you're interested in. So if you're interested in you know, the energy efficiency level of vehicles, then you need to think about the number of miles per gallon or miles per kilometre, whichever metric you're using, and then all the other factors which leads to that. So it could be make, it could be size of the car, the weight of the car, it could be the size of the engine, it could be all these different things, right? And then you kind of want to understand how those vary against this one output metric that you want, and correlation is a really good way to do that. So getting back to the point, we can then kind of encapsulate those different dimensions based on how two variables change. So imagine we've got the x-axis here and the y-axis, Here, in this particular case, as the x-axis values increase, we get a similar increase in the values on the y-axis. Okay, so this is called a positive correlation. So for every one unit increase in the x value on the x-axis, you get a corresponding positive increase in the y-axis value. Okay, and that's why it's called a positive relationship. Because if we look at the kind of reciprocal of that, the opposite, the negative, well, for every one value increase here I get on the x-axis, we're actually getting a decrease in the y-axis value. Okay, so this is negatively correlated, because if we increase the x by 1, the y-axis value would actually decrease. In this case, it's negative. Okay, so here we've got a positive correlation, here we've got a strong negative correlation. And then also, what often happens is you might just have two variables that are completely unrelated, okay? And you might just plot them, and there's just no correlation between them, okay? So essentially, you might say that that's neutral, and that's kind of our null hypothesis here. When we actually start testing correlation strengths, is just basically that the two variables aren't related in any way, okay? So the strength. So these are both positive correlations here, okay? But the difference is that this is a strong positive correlation, whereas this is what you would call a perfect association, okay? So for every 1 unit increase in x, we get a 1 unit increase on the y-axis. Whereas over here, maybe for every 1 unit increase in x, we get a 0.7 or 0.8 unit increase on the y. Down here we might have what we call a weak association, so this has been flipped from positive to negative, but it's kind of making the same point, which is that here we get a weaker association. Okay, so for a 1 unit increase in x, we might only get a 0.3 unit decrease in y, okay, this time because we've got a weaker association with the y-axis. And then in the case of this no association here, we might get a 1 unit increase in x, and it might lead to a 0 or just kind of a piece of random noise increase on the y-axis here. Okay, so there's really no relationship whatsoever. So essentially correlation values can be 1, as they are here with the perfect association, or if they were perfectly negatively correlated, then it would be -1. 0 implies no correlation, so that's where we are over here. And then we get variance elsewhere within that kind of range. Okay, so 0.7 here might be a good way to kind of understand that. And over here, if you had something that was maybe like -0.5, you might get something like this. Okay, so we'll go more into that later. But essentially, on the correlation side, we have this kind of association that we're looking at between the two variables, right? So those variables could be linearly correlated, so they follow a straight line pattern, much like this perfect association that we have here, or this strong association, or indeed the weak association. They're all linearly correlated. We could have non-linear, so it could actually be curved, and we'll look at that later. Or we could just have a random distribution, okay, so no trend between those two variables that we're looking at. Our tests that we're going to look at here actually measure the linear association, okay? However, there are some important things to remember, okay? So you might have encountered this before, but basically just because you have a correlation between those two variables, it doesn't actually mean that they're causal on each other. So what does that mean? So what that means is just because x and y vary together, it could be entirely by chance. It doesn't actually mean that x is driving y, okay? And x is the reason for y's increase. And this plagues these kind of techniques. So you'll always kind of come across this old adage when you start getting into using these in reality. And that's just because you could correlate quite strongly a whole load of things that are completely unrelated to each other, okay? It doesn't mean that they're causal in any way. So if you look at the use of Internet Explorer versus the murder rate, so imagine this is the murder rate here, based on these. So 2006 it was around about 17,000 people, and then by 2011 it's down to below 15,000. Equally, Internet Explorer, Microsoft Internet Explorer penetration was around 75% in 2006. Now it's below 40%, okay, in 2011. So essentially the point is these are highly correlated with each other. But obviously there's absolutely no relationship between the two of them. There's no causal effect, which is meaning that as people stop using Internet Explorer, they're also less likely to also murder people. Okay, and you know, there's some really funny stuff that's out there. You can look at all of this on the internet, but if you look at the number of people who drowned after falling out of a fishing boat over this 10-year period and the marriage rate in Kentucky, you get this pretty much similar, quite highly correlated time trend. Okay. And, you know, I just want to put in a couple of stupid graphics for you here, and obviously this came off kind of the geeky Twitter sphere that I'm part of. And I just saw this and thought it was really funny. So yeah, it was one of those classic, you know, correlation does not imply causation memes. And obviously you've got this kind of broken roof here and the cat sitting on top of it. Just because the cat's sitting on top of it in that central position, it doesn't mean that the cat has actually caused it, okay? And the same for the duck running through the gates. I always feel like this is always a little bit Harry Potter with the big kind of broken gates at the front of Hogwarts like this. And obviously the ducks run through, but it doesn't mean that the ducks obviously broken those gates. These are independent events in you. As a consequence, you need to apply your logic when you're using these techniques, and just be aware that just because they're correlated, it doesn't mean they're actually related to each other or driving each other. Okay, and the same happens with spatial variables, but there may be other variables that you might be missing out. Okay, so I just need to kind of discuss this with you. So it's always a problem, you know, have you accidentally left out important variables which are having some sort of impact on the actual data results that you've obtained. So we need to kind of discuss this a little bit. If there are multiple variables in a data set, we have similar associations, then there may be a problem of multicollinearity as well. So I'll pick this back up next week, but generally you get this within geographical problems. So if you have wealth and you have population density, you're probably going to end up having quite strong multicollinearity within those, and that's because generally where the population density is higher, you also have higher per capita wealth, okay, because that's where, you know, if you're thinking about high population density areas, that's cities are where you have most industrial activity, and as a consequence per capita incomes are much higher there than low density areas where generally you're probably going to have more kind of agricultural or natural resource based economic activities, and therefore lower per capita incomes. The point is that you don't want to have lots of variables in your regression, as I'll explain at a later date, which all vary in the same way, because then you're not actually providing much additionality to the model that you've got. Okay, so I'm not going to go into too much detail about multicollinearity at the moment, but you need to be aware of it, particularly when we move to next week. So as a geographic example of how correlation does not imply causation, okay, so here I'm using one that's relative to my home. So these are areas that voted to leave the European Union, otherwise known as Brexit, so Britain leaving the European Union, and then also those areas which basically had a high prevalence of mad cow disease, okay, so this is bovine encephalopathy, I think was the actual name for it. But essentially what you have here are two very similar maps, right? Okay, and it's kind of funny that they geographically look very highly correlated. But actually the reason why they're like this is that you have other variables which are kind of driving the outcomes, okay? So the BSE free areas here are basically parts of Scotland, some parts of Ireland, and some parts of England, okay? The BSE free areas here, sorry, the BSE areas here are the darker shades, okay? So this is like parts of the northeast England, eastern England, some parts of Wales, the southwest, and just a very small part of Northern Ireland. And then if you look over here at the places that voted to leave, so voted for Brexit, for the UK to leave the European Union, they're all in this dark blue colour. And then the places that voted for a majority to remain were all in this yellow colour, right? So the point is that there's other variables which are basically driving this. So for the BSE issue, what was happening was cows were being slaughtered, and those cows were having the meat taken off and they went off into the food supply chain. And then when there was leftover body carcasses and things like this, including the spinal matter for the actual cow, it was put back into the food cycle. And this seems crazy now, but that's basically what happened in the 90s, right? So even some of the spinal cord area where this BSE disease existed, it would go back into the food for the animals basically, and it ended up meaning that they had this this spread of this disease, and it affected the brain, and basically it meant that there was the brain would stop functioning properly in the cow, and also it would spread to humans if the humans ate the meat that was bad. Okay, and so basically those areas here that are in dark, which are the areas with BSE, they're actually the areas that have the lower per capita income relative to some of the other places. Okay, so these are some areas of deindustrialization in the northeast. This is quite like those areas around like Detroit and things like this, where maybe you don't have quite so much economic activity anymore. There's a lot of unemployment. People may be eating the cheapest meat that was available. And then those other areas here where the BSE free areas are, they may be wealthier areas, you know, the outskirts of London, parts of London, where people are maybe richer, they're able to buy better quality meat, and as a consequence, they weren't affected in this way. And then when you get to the Brexit vote, it kind of fell down quite similar socioeconomic lines. Okay, so if you live in an area that's wealthy and had more young people, then you were more likely to vote to remain as part of the European Union. And if you were actually in one of those areas that was maybe older or maybe less socioeconomically advanced, then basically you were more likely to vote for Brexit, okay, vote to leave. So you end up with these two very similar maps, which is interesting, but they're actually being driven basically by socioeconomics and demographics. And if you just looked at the maps on their own, you would assume that they were correlated, but they're not, okay? This is because we have other variables which have been left out of the model, which we need to consider. So that's kind of like the health warnings for these tests, okay? Because, pun intended, by the way. So they're kind of the health warnings. So it's like, these are cool things that we can do, but you have to be aware that they come with these caveats, like correlation doesn't equal causation, and that you might leave other variables out if you just focus on two main variables, for example. Now I'm going to get into kind of how we would apply this, right? So covariance here, this is basically a parametric correlation. And basically what we're able to do is we're able to measure how much two different variables actually vary together, okay? So here, this is basically just like the positive correlation, strong positive correlation that we looked at previously. We can look at the covariance between these. We also have this relatively negative covariance over here, so negative correlation, strong negative correlation as well. And then we have basically low covariation here, which is where we essentially have no relationship between these two variables. So how do we get this CVXY here, this covariation for x and y? Well, basically we need to take the deviation of x from its mean. So remember, x bar is the mean value, and then we're going to subtract it from each of the x values. And we're going to do the same for the y values. So we take the y bar, which is the mean, and we subtract it from the y values. And we multiply them and sum them together to get the covariation. Now remember that these types of mean deviations we've used in many other places, so whether that was standard deviation or standardized scores, you should be quite familiar with this type of calculation now, okay? So that's a little bit of background to covariance. In the next tests, we're actually going to pick up on that because it's kind of one of the basic techniques that we use for actually measuring those differences between the variables. So here, the first one we're going to focus on is the parametric version, which is Pearson's product moment correlation coefficient, and then shortly we'll focus on Spearman's rank, which is the non-Gaussian, non-normally distributed data, non-parametric version, okay? And what's interesting about this is that you saw that we had that covariation calculated previously, and we actually calculate it, or we use it again in this particular process here, okay? So here we're focusing just on the multiple ways that we can calculate the parametric correlation. And when people usually say correlation, what they're usually meaning is Pearson's correlation coefficient. It's just shortened. Okay, so I've not referred to it so far as Pearson's, but essentially when we do refer to correlation, that's basically what we're saying. So we want to get this Rxy, which is the Pearson's correlation coefficient. We will need the standard deviations of x and y, which you guys know how to calculate now by hand and also in R, so that's easy. And then also this n number here, which is the number of paired data values. Okay, so it's just the total number of data points overall. Total number of paired data points that we've got. So the length of the data frame. So to get our Pearson's correlation coefficient here, what we can do is we can take the CVXY covariation metric that we produced previously, divided by the number of paired data points that we've got, and then we divide it again, once we've got that numerator, by the standard deviation of x multiplied by the standard deviation of y, and that produces this R. And we can calculate that in a more complicated way if we want. So if we want to do it rather than doing it in separate steps, you want to do it in one giant equation, well then you can basically sum x and multiply it by the sum of y and divide it by the total number of data points and subtract it from the sum of x multiplied by y. And then basically what you can do on the denominator part of the equation here is to find the standard deviation for x and the standard deviation for y. So I'm not going to talk you through that because you know how to do it already. But basically there's multiple ways we could do this calculation. We're going to get this R value here. So once we've got that R, what do we do? Well, we're able to then actually statistically test whether this is a significant finding or not. Okay, so the objective is to determine if the association exists between two variables to some sort of significant level, for example 95% confidence, or whether this association has just basically randomly occurred by chance. So we need to meet those assumptions for the test. So we need to have random sample of paired variables. We need to have some sort of linear association between the variables. So it's a good reason why you need to look at those pairings beforehand to look at the relationships visually. We need to have interval or ratio sample observations, so that's obvious because this is parametric. And then the two variables need to have a bivariate normal distribution, okay? So they need to be normally distributed. Hypotheses, so basically this is the Greek letter rho here, and what we're basically saying is that rho is equal to 0, okay? So the null hypothesis assumes no correlation between the two variables. Whereas the alternative hypothesis here, we're basically saying that rho is not equal to 0. And this is the two-sided approach. So remember, this isn't where we say it's larger or it's smaller, we just say they're different. And we're not sure how they're different, but we think that they could be in either end of the distribution. So I know a few of you kind of tripped up on that in some of the previous work. So just remember when you state your hypothesis, whether you are expecting it to be two-tailed, as we are stating here, or whether we think it's one-tailed, okay? If we have some sort of a priori knowledge that we think that rho might be larger than 0 because we think they may be positively correlated, or in this case, if we think rho may be smaller than 0, then maybe we think it might be negatively correlated. And we'll have to use our kind of intuition as to whether we think one of those one-directional approaches is appropriate for us, and then you need to make sure you get the right function in R and then actually tell it whether it's one-tailed or two-tailed, because I noticed in some of the homeworks that was kind of the issue that we had. Some of you had kind of taken the function, but you hadn't changed whether it was one-sided or two-sided, and it was set up incorrectly and it gave you the wrong result, unfortunately. So obviously in those cases I gave you half marks for working out because you basically got the right interpretation for the test and the code, but what you didn't manage to do was kind of set the function up correctly. So you need to make sure you manage to do that in the future. Okay, and then we can just use the T-Test statistic, and we can do that basically by taking that R value that I mentioned before, multiplying it by the square root of the number of degrees of freedom. And obviously the number of degrees of freedom, as we've got two metrics here, is going to be n minus 2. And that gets our numerator, and then for the denominator we can take the square root of 1 minus R squared, okay? So the sample correlation coefficient is R, and is the best estimate of the population correlation coefficient rho. Great, so that's what happens when we've got nice, normally distributed data. What happens when we don't? Well, basically, if we've got non-parametric data, then we may look at using Spearman's rank correlation coefficient. Okay, so this is what we apply when we've got monotonic relationships, whether linear or not. So functions are known as monotonic if they are increasing or decreasing in their entire domain. So convert to rank data to basically make it linear, all right? So this is maybe what we were testing previously, linear monotonic data, but then we might end up with monotonic non-linear data like this, or non-monotonic data. here. And so we need to basically be able to kind of flex the statistical toolbox that we've got to address some of these situations. So basically we have this D value here, which is the difference of the ranks in variable X and Y for each paired data set of values. And then we have N, which is the number of paired data values that we've got. So we can essentially get this RS, so it's the R value for Spearman's rank. And basically we want to get the numerator first, which is 6, multiplied by the sum of the difference in ranks for X and Y squared, so it's the sum of the squared difference. And that gets our numerator, and then we can divide it by the number of paired data values cubed minus N, again the number of paired data values. And then once we've got that, we can subtract it from 1 to get our S value, okay, so Spearman's rank. So the objective is to determine if there's a correlation between the two variables. We have some requirements. We need to make sure that our data are randomly sampled and that they are paired variables. And we need to make sure that we've got ordinal data. So if we've got non-parametric data which is continuous, we need to then downgrade it to interval ratio data. And then we basically need to take I need to make sure that we've got two paired variables X and Y and that we have a monotonic relationship. So how do we specify the hypotheses? So here we have the null hypothesis, and we have the row value of S, so Spearman's row here. In the null hypothesis, we're saying that these that there's basically no correlation, okay? So we would expect that the row S value that we get is the same as 0. So that would be indicative of no relationship and no correlation. Whereas the alternative hypothesis here is basically row S, and we're saying that it's not equal to 0. So this is the two-sided variant. So we're not saying whether it's larger or smaller, we're saying it's just different. And therefore we need to account for the fact that we think it might either be in the top end or the bottom end of the distribution, but we're just not sure. So you need to make sure you address that in your test. Or we could have a directional alternative hypothesis, which is just one-sided. So here we could say we think that the row value is going to be larger than 0, so we think it's going to be positively correlated. Or we think for the alternative hypothesis that the row S value here is actually less than 0, and therefore it could be negatively correlated, we think. And we need to get Z or T in the case of us having a smaller distribution than we would like. So the Z value, obviously we need to have maybe 30 or more data points for that. But essentially we want to have the Z value here that we get by basically multiplying that Spearman's rank correlation coefficient RS here by the square root of n minus 1. Okay, and that gives us this ZRS value. Okay, great. Well, it's not a long session this week, and just a couple of tests for you to look at, which is great. So I'm going to go over these within the R Studio session shortly, and then you've got plenty of time to basically go over the lecture slides and the R content at your leisure, and hopefully carry out the assignment that I've set for you and get that in on time, preferably before the Thanksgiving break. Okay. So look, it's been nice to speak to you again, and do reach out to me if you've got any further questions, and I hope that you enjoyed the session today, and I'll see you in the laboratory session. All the best. Thank you very much. Goodbye.